Assalamualaikum and hi. My name is SYSZARINNA binti OMAR from Bachelor of Technology Electronic Engineering Electronic System with Honors in University Malaysia Perlis. Today, I want to explain about my assessment for subject Analog Electronics 2. Introduction. An operational amplifier, or OM for short, is fundamentally a voltage amplifying device designed to be used with external feedback components such as resistor and capacitor between its output and input terminal. These feedback components determine the resulting function or operation of the amplifier, and by virtue of the different feedback configuration, whether resistive, capacitive, or both. The amplifier can perform a variety of different operations, giving rise to its name of operational amplifier. Question 1. To illustrate what an operational amplifier is, we need to consider its ideal characteristic. A. Explain what an ideal operational amplifier. B. Distinguish the properties of a LM741 to those of an ideal OM. Ideal operational amplifier, if you see in circuit, we have negative and positive input, negative positive voltage, and also output. The ideal operational amplifier is an amplifier with infinite input impedance, infinite open loop gain, zero output impedance, infinite bandwidth, and zero noise. It has positive and negative input, which allows circuits that use feedback to achieve a wide range of functions. The characteristic for LM741 and ideal is LM741 has open loop gain of practical operational amplifier is around 100,000, and ideal has infinite voltage gain, non-zero offset voltage, while ideal has zero offset voltage. LM71 has very small value, while ideal has infinite bandwidth. LM741 has zero output impedance and infinite input impedance, while ideal has output impedance is in the orders of 100 and the input impedance is in the orders of mega ohms only. Question 2. If the operational amplifier were perfect, the ideal step response of operational amplifier will be produced. In practical, however, the output is the exponential with a certain time interval. A. Show an operational amplifier with an input voltage step and its resulting output voltage that related to the slew rate. B. Explain what is slew rate, it is important, and define your answer. Okay, this is circuit for regarding to slew rate. Slew rate of the operational amplifier can be defined as the maximum rate at which the output of the operational amplifier can change. Or in another way, we can say that how fast the operational amplifier is able to respond. So let's say we have one operational amplifier which is configured as voltage follower. That means the output of the operational amplifier will follow the input signal. Okay, here we have 10 volt and 11 kilohertz, 11 kilohertz, and we use 12 volt. Okay. The output will take some time to reach from 0 to 10. Have a microsecond, the waveform will look like this. So the time which is being taken by the operational amplifier to reach 1.45 volt microsecond depends upon the slew rate of the operational amplifier. For the general purpose solvent for 1 series operational amplifier, the value of slew rate is 0.5 volt microsecond. So, if you see here, delta out, delta V out over delta time, so 90% maximum voltage minus by 10% minimum voltage over T maximum minus T minimum. So I got here 1.5 volt microsecond to get the graph like this. Question 2. If the OM were perfect, the ideal step response of OM will be produced. In practical, however, the output is the exponential with a certain time interval. A. Show an op-amp with an input voltage step and its resulting output voltage step related to the slew rate. B. Explain what is slew rate, it is important, and defend your answer. Okay, this is circuit for slew rate. Slew rate of the operational amplifier can be defined as the maximum rate at which the output of the operational amplifier can change. Or in another way, we can say that how fast the operational amplifier is able to respond. So let's say we have one operational amplifier which is configured as voltage follower. That means the output of the operational amplifier will follow the input signal. Okay, here we use 10 volt and 11 kilohertz and 12 volt. The output will take some time to reach from 1.5 volt microsecond. The waveform will look like this. So the time which is being taken by the OM to reach 1.5 volt microsecond depends upon the slew rate of the operational amplifier. For the general purpose 741 series operational amplifier, the value of slew rate is 0.5 volt microsecond. This is the formula: 90% of maximum voltage and 10% minimum voltage. So I got for 90% maximum voltage is 9.23 volt, while 10% of minimum voltage is 1.13 volt. Okay, we have to minus 90% max volt minus 10% minimum volt. So I got 8.19 volt, and per time maximum minus time minimum. So I got 5.51 microsecond, and we got 1.5 volt microsecond. So this is the waveform, and the slew rate is important because the slew rate help us to identify the amplitude and maximum input frequency suitable to an operational amplifier such that the output is not significantly absorbed, distorted. Question 3. Give an example of an inverting amplifier using an operational amplifier with component values and explain. A. Where the visual ground is. B. The properties of a visual ground. C. The closed-loop voltage gain and input impedance. This is the circuit for inverting amplifier. If you see here in the circuit, we have 1 volt. We use 1 volt and 1 kilohertz. Our feedback 10 kilo ohm. Resistor 1 kilo ohm. And we use 15 volt. Okay. In this circuit, inverting amplifier, we want to know where the visual ground is. It's in here. Okay, this is the visual ground. What is visual ground? Concept of visual ground is only meaningful for operational amplifier circuit of closed loop configuration. After all, operational amplifiers are different amplifiers with infinite gain. Hence, visual ground is for the case when feedback circuit act to control the voltage difference between the two terminals small enough to make the output linear and below VCC. Properties of visual ground created automatically by the feedback action of the operational amplifier, and the negative feedback path is provided by R feedback or capacitance. Closed loop voltage gain, so this is the formula for gain, negative R feedback per R in, so we got negative 10 kilo ohm over 1 kilo ohm, and we get negative 10. So closed loop, the operational amplifier try to match the two input terminal equal by supplying a potential to the inverting input terminal. Input impedance is X approximate equal to resistance. Question 4. Construct a summing amplifier and then summarize the theory of operation. Summing amplifier can be used for the operation of addition, averaging, as well as the scaling. Apart from that, it can also be used to provide the DC offset to the input signal. Likewise, this inverting summing amplifier can also be used for the digital to analog. And apart of that, it also can be used for the mixing the different audio signal. So, these are the different applications in which this summary amplifier can be used. Okay, if you see here, this is the formula for summing amplifier. Negative Vout equal to R feedback per R in multiplied by V1 plus RF feedback per R in multiplied by V2 plus R feedback per R in multiplied by V3. Now, theoretically, we can add the n number, which is a resistor here, R1 and R2, of input voltage to this operational amplifier configuration. But practically, if you see the number of input voltage depend on the power dissipation, as well as the total current that can be supplied by the operational amplifier. Because here, if you see the total current, if it's the R1 and R2, summation of the individual currents. So this value should not exceed the maximum value. That's all from me. Thank you for watching.